Yeah, I'll just share my screen. Yeah, is my screen visible now? Hello?
Yes, yes. I think it is
Yeah,
visible
yeah.
now.
Okay, okay. So thank you, Shubham, for the introduction. So we'll start the session by just giving some small introduction about the people around us. We can start with I think Tanish Mehta. Just give a small brief, 2 lines about you, and then we'll move. We'll start the session. We'll take like 2 minutes for that.
Good afternoon, everyone. Myself, Tanish Mehta. By profession, I am a student, an engineering student. As my father has an EV showroom, I got this idea of this session, so I have joined it. Basically, I and my group have done the patent in EV sector only as our
Okay,
project. So I
okay,
have the interest in this.
okay, okay. Thank you, Tanish. We can go to Manoj ji, if I'm saying the words correctly. Manoj ji, Ghosh.
Yeah,
Yeah,
hi Ajay,
yeah.
Manoj
Hi.
Ghosh. So we work around electric vehicles. We
Okay,
particularly build electric pickup trucks,
okay,
and yeah, our company is Axelo Innovation Private Limited.
okay,
I came across this masterclass in LinkedIn, so I thought I should give it a go. I
okay.
just want to learn about more into battery and
Sure.
those stuff around. Yeah,
Sure, sure. Like my voice is audible to you guys, right?
yeah, yeah. Yes.
Okay, okay. Now next is Kiran Kumar.
Yeah, myself, Kiran Kumar, sir. I am in
Hi.
electric vehicle business. Hi, sir.
Okay, okay.
I want to more about EV batteries from recent
Sure.
technologies.
Okay, okay.
Yes, sir.
Great, great, great. I think next is Mayappa SB. If I'm not right, please forgive me for misspelling or mispronouncing any name. So yeah.
Yeah, that is fine. Yeah, hi. My name is Mayappa SB. I am from Bangalore. I'm working in Connectem Technology as a
Okay,
software engineer. So
okay,
I'm working in this EV platform from last 6 7 years.
okay.
So I joined from this Connectem.
Sure, sure. That's great. Okay. I think Gopinath Ji next.
Hello, everyone. Hello, Ajay.
Hi,
Uh,
hi.
I'm an embedded software engineer over the last 6 years. Over
Okay,
the last 3 years, I'm in battery management system, so I want to learn the entire ecosystem about the battery chemistry as well as how they are handling and how they are operating, like this kind of scenarios. I
sure.
want to know so that I have come here to attend these sessions.
Okay, okay, sure. Okay. Next is Manthan Nayak.
Hi, sir. I'm Vindhan Nayak from Billimora, Navsari.
Hi.
I am a trainer at Serval Automobile in established in Billimora. We are serving many franchises two-wheeler service.
Sure, sure. That's great. That's great. I think next is Deepak Kadamji.
Myself, Deepak Kadam from Cabelius Technologies India Private Limited. I'm
Hi, sir.
already into EV field, EV chargers. We are
Okay,
into EV chargers, and I want to learn about more about batteries and all.
sure, sure. Next is Vikasji.
Hi, I'm Vikash. So I'm a student and I did my project in the field of batteries. So
Okay,
I just wanted to learn more about this field and then say join this course.
sure, sure.
Yeah.
Okay, next is Naveen. Naveen. I think, am I audible to you guys? Hello.
Yeah, yeah, you are audible.
Okay, no problem. Okay, can move on to Chaitra. think they have muted or something. Okay, next is Swati Sahu. I mean, if we make it interactive, then we'll be able to learn more.
Hello.
Yeah, hi.
Yeah,
Yes,
I'm
Swati.
audible. Yeah.
Yeah,
Yeah,
yeah.
hi, this is Swati Sahu. I work as scientist at TCS Research, and I've done research in battery chemistries and modeling. For the masterclass, I want to understand the real what are the real situation, what are the real
Sure,
challenges in
sure,
EV
sure,
batteries. Yeah.
sure. Okay, I think the last is Yash.
Yeah, hi. I am Yash Dama from Valsad, Gujarat. I am also working in electric vehicle field from 2020, and I am involved more in related to service and training of electric two-wheelers mostly.
Okay,
Now, mostly I had means motor controller, charger, and all that, but I now exploring for the battery diagnosis part. So
sure,
from last short of time, I am seeing your company's data and all that. So
sure.
just
Okay. Thanks a lot, guys, for the brief introduction. I'll try my best to make this more fruitful for you guys. So, as Shubham has introduced me, like I've worked with DRDO, I've worked with different type of embedded systems and all, which helped me to build this product that we have built, EV Doctor. I'll talk about that later, but first we'll start with the masterclass now. So, my screen is visible to all of you, right? I've shared
Yes.
my screen. Yeah. Okay. Done. So we'll start with the brief of batteries. Since the heart of an EV is the batteries, so we'll start with a small brief that how batteries came into picture. So Benjamin Franklin first coined the term battery, and then after that, the lead acid came into picture in around 59, and then in 99 cadmium batteries, and in 1992, where the Nobel laureates were given Nobel Prize for introducing lithium battery with the smaller pack size, right? Since then these chemistry has been fixed, but the forms has been changing around it. Okay, according to the application it is being applied to. Okay, now we'll move on to like what is the basic component of an electric battery. So where then there are two things that are there, an anode and a cathode. Be it any chemistry, let's suppose if we talk about lithium ion, sodium ion, or any kind of a chemistry, the basic chemistry suggests there would be an anode and there would be a cathode. So now anode would have a chemistry. So let's suppose mostly in the lithium chemistry, graphite is used for the anode side, and on the cathode side, mostly lithium, nickel, cobalt are used. So if we talk about the commercial part of the battery, the cathode owns that thing, and the charging time for a battery is being owned by the anode. Okay, and in between any of these two chemistries there is a separator which makes sure that the battery doesn't discharge itself, or it has got some rate of discharge or some sort of resistance between the anode and cathode. So basically these are two chemicals that are being separated by a layer between it. Okay,
Oh,
sure. Now we'll move on to some basics. So since it's battery, so voltage, capacity, energy, power. So these are the most common terms that are being used when you're talking about a battery. So it doesn't matter what kind of a battery chemistry it is, voltage, AH, energy, power density. Whenever you go buy a battery, the basic things that you'll get about this cell, the battery pack would be either the voltage, what is chemistry. After the chemistry, of course, the electrical parameters would be voltage, AH, energy, and power density. So let's brush up upon the basic things, what actually voltage is. So when we talk about voltage, so but voltage defines. So there are 2 points. Let's suppose there are two energy levels that are there. So one it is at a higher point and one it is at a lower point, right? So when the current flows between from a higher potential to a low potential, to take an example of a river flowing from a cliff to the ground, right? So the cliff is at the top and the bottom is at the ground, right? So that is the higher potential and the ground is the lower potential. So the energy flowing from the top to the bottom is defined as a voltage in the electrical terminology. Okay. So basically it is a potential difference between 2 points. So which decides how the electrons would flow from anode to cathode, right? So in the SI unit for it is volts. Whenever you go buy a cell, they'll always tell you, either you ask them and they'll tell you that which type of cell do you want. The first terminology used at that point of time is for NMC, the nickel NMC that I'll explain later. but NMC and LFP are the two types that are there in the lithium chemistry. So 3.7 volts is being used for NMC, and for LFP 3.2 volts is being used. Okay. So then the second terminology is capacity, which is either defined by ampere hours. So basically, what happens is when you charge or discharge a cell or a battery pack, the governing electrical parameter is called as capacity. So if you take an example of a glass, how much that glass can hold of water is defined by capacity, right? How much what you can say rotis you can eat at a one sitting is defined by capacity for a human being. So similarly for cells or battery pack, AH is defined by that. Okay. So here's an example of when you've got a 10 Ah battery, theoretically it will deliver 10 amps to 10 amps for a 1 hour, or if you draw 1 ampere for 10 hours, it can deliver 1 ampere continuously depending upon the load. Okay. Now we'll move on to the energy density. So energy density is defined by the amount of energy per unit stored in a mass. Okay. So this is basically when you're buying a big battery pack, then at that point of time, people talk about what is the energy density, what is the kilowatt hour you'll get out of it. So that is there. So whenever you go buy a battery pack, they'll talk about energy density or power density that is there. Okay. Later, now the power density. So power density is just how fast the energy can be delivered per unit to the load. Okay. Now we'll brush up the basics that we have learned right now: voltage, capacity, energy, power density. So these are the things that you should know whenever you are trying to know about battery packs. You don't need to know. I mean, if you go in more depth, you'll have to understand what are the chemistry that are there in the anode or in the cathode, or what are the type of material that are being used for the separator. But we'll go through the basics of electrical parameters that are there with the battery pack. Later on, it will be discussed in more detail on the slides. Okay. Now, whenever we talk about lithium ion, so as you know, around I think 2004 or 5, sorry, not in 2004, 2008 or 9 around, there was a major incident where the S4 or S5 Samsung was recalled all over the world. So the case was that the batteries that were used were unsafe, and that's why that particular model from the Samsung were never allowed to, or the passenger having that phone were never allowed to board the aeroplane. So after that, the safety came into picture with the lithium batteries, right? So we'll talk about the basics of how to handle lithium ion battery. So throughout the journey, I've met different kind of people who are into servicing, who are into building battery packs. So one of the things that we have learned about how the users are using lithium ion battery pack, they try to touch all the things that are there in the open by their bare hands. So let me tell you that anything that has got electrical parameters related to it, never to touch it directly via your hands. I mean, we never know what kind of static charge you are carrying, or we never know what kind of electrical voltage or current would pass through your body, which would be very harmful for you and which would be very dangerous for you. Okay. So always remember, whenever on any kind of a battery pack or the BMS or any sub part of it, if it is an open electrical connection, never touch it. So going deep into the lithium ion battery pack, every time you go and buy a new lithium ion battery pack or testing equipment, so always check whether there are proper insulations provided over to the pack as well as or to the charger or to the equipment that you are buying related to your battery pack. Okay. Am I audible to you guys? There is no jitter in between.
No, it's perfectly all right.
Fine.
Audible.
Yeah. So the major basic problems that are happening because of these things, that when we are handling electrical appliance, could lead to causes like thermal runaways, fires. Even it can cause the BMS not to perform properly the way it should perform. Okay. So I'll talk about those things also into the later on phase of this now. Okay. So LG has had issued 12 tips how to use the battery packs that you are having, be it for EVs, be it for any kind of application. These are the 12 parameter tips that they have provided. Always make sure that you never ever overcharge or discharge your battery pack, because most of the incidents that are happened is because of overlooking the charging or discharging of the battery pack. It might not always be the case that it would lead to some hazardous condition, but it would definitely lead to the battery either being I mean not applicable for that application, or it may not give you the kind of you know what you can say, the kind of performance it should give, it won't give. Okay. So all these things that are there would be provided to you, as I think Shubham might have mentioned. So you can go through it. I'll not go into the small details. These are some basics about like how to handle a battery. Now, whenever you go out and buy for any kind of an application, so we'll be specific to the EV right now. So there are two types of chemistry that you'll find in the market or maybe in any hobbyist shop. So that would be, one is LFP and then the other is NMC. So LFP is basically lithium iron phosphate, and the NMC is nickel cobalt based basically chemistry, right? So both of them have got their own pros and cons. So let's suppose if you want to have for an application where you have got a dirt bike, where you have to take the dirt bike uphill, so you need a higher torque. So for higher torque application, you'll be going for NMC because it has got a smaller in a smaller what you can say, smaller pack. You'll have more energy density, right? Whereas for, let's suppose if you want a longer life run, so you'll go for LFP. So for, let's suppose if you want to have a electric three wheeler, you want to have 100 kilometers of range, and for a longer run you want it to run for 5 to 8 years, then you'll go for an LFP kind of an application. Right now, most of the application are shifting from NMC to LFP, but there are few applications still who are using NMC. And since these two have got their own set of pros and cons, according to your application, how what you are developing, you'll be using it for that. Mostly NMC is used for if you have got a very wide requirement of power and energy, then you'll be using for NMC. But for a higher cycle count, you'll go for LFP. Okay. Yeah. So this is some basics about the battery. So all the kind of chemistry that are available with the lithium chemistries are there. Okay. We'll start with the first one. I hope this image is visible to you guys. I'll just zoom into you. Okay. Yeah. We'll start with the NMC. So as I've told you, for your application, according to your application, so you'll need a specific energy, specific power. You need in some application you'll need safety. So let's suppose if it's in a flight kind of an application, so you'll need a safety out there also. So somewhere you need the balance of both the safety as well as the energy and power. So you'll need a performance out of it. For a longer lifespan, you'll have this application. So these are the parameters that you go through when you are buying a battery pack for your own application or building or designing a battery pack for your application. You'll have to have these parameters into consideration when you're using it. So we'll start with the first NMC. That's the most common. Whenever you go out in the market and you'll ask for a lithium ion battery, mostly they will offer you an NMC kind of a battery pack. It won't be specifically mentioned that it's an NMC, but they'll always say that it's a lithium ion battery pack, right? Whereas similar kind of is NCA also. So I'll start with again with the NMC. So if you need as I've told you earlier as well, if you've got a high energy or high application or high power kind of an application, then you'll be using NMC. Now, whereas it will have a mild cost to it because it has got a smaller, you can say, pack size, and you will have a bit more energy out of it, right? So next is the NCA, which is called as lithium nickel cobalt aluminum oxide. It has got a good application, but mostly it is being used for let's suppose for a long range EVs. It is being mostly used, right? It is also similar to nickel cobalt because the charging curves always follows the similar kind of a thing. But for LFP, it's a different kind. But NMC and NC are almost following the same charging curve as well as discharging curve. Okay. Next is lithium ferrous phosphate. Okay. As I've told you, the most safest is now considered to be LFP, and almost all the application is shifting towards LFP because of the kind of situation for NMC is offering. It has got more energy, but the safety is a concern for on that side. But there are few forms that are available for NMC that can be used for that kind of an application. So for the LFP, the safety, the specific power you get is the maximum. In the lifespan, if you expect like for NMC, if you get around 1,000, you get almost 2,200 cycles out of LFP. Okay, next is LCO. LCO is a similar kind of an application like NMC, but the performance that you want for an application would be less as compared to the other chemistry that is offering. And similarly, lithium manganese oxide. Okay, now yeah. Next is now, as I've told you, these are the two chemistry that are being used most widely all over the world, LFP and NMC kind of. And these are the you can say the providers or the manufacturers of LFP and NMC cells at least. So there is LG, there is Enersync. For NMC, there are One Charge, Nevitis, and Sol Technologies. So as I've told you, LFP always offer around 2000, almost double the cycle of NMC, but the power that you'll get out of LFP would be less as compared to NMC. So whenever you start, now you have selected what kind of a, for a battery pack design, what kind of chemistry you're going to use. Now we'll have to design the battery pack. So cell is the smallest unit for a battery pack. Okay. So let's suppose we have got a Samsung 18650. That's the cell form factor. So why it is 18650? Because the length you can see here is 18 meter and the breadth is around 65 millimeters, right? So that's why it is called an 18650. Okay. And and it's an NMC type of a cell right now, and it is offering you around 3.7 volts. That is the voltage, as I've told you in the first when we were talking about the electrical parameters. So that's how it is being defined. So there are three types of voltages that are there. That is a nominal voltage, there is a upper cutoff voltage, there is a lower cutoff voltage. So whenever you go buy a cell, they'll always offer you a data sheet in which they will define what is the nominal voltage, what is the upper cutoff voltage, what is the lower cutoff voltage. These data sheet helps you to decide what kind of for your application what kind of cells would be there. So if Samsung is providing you at 3.7, let's suppose if you go to LG, they'll give you a 3.6 volt. So according to the way they have manufactured their cell, they'll offer you the data sheet in which they will define the nominal voltage in it. Okay, and then the next thing that you get the capacity, that is the 2.6 Ah. So how much is the energy that we can get out of it? This will be defined the chemistry by the capacity. Okay. Now when you're making a battery pack, so there is one thing called as series pack combination. So if you might have, if you can remember the physics in 11th and 12th, you might have studied about keeping the cells DC sources in series and parallel. Now, when you connect two cells in a series, okay, so let's suppose if it's a 3.7 volts, and if you connect one more 3.7, the overall voltage gets added up. Whereas if you keep them in series, the overall voltage would remain the same, but the current would get divided. Okay, so this is the series combination. Okay, and of course in this you'll have to make sure that the polarity is always the same, because that is what we have taught in the 11th or 12th physics. Now in this case, this is what we call as 2p1s kind of a battery pack. So if you take only a single, that's a cell, and if you take it in kind of a combination of series parallel, then you get a battery pack out of it. So this is a 2p. That means there are two parallel paths, but it is in a single series. That's why it is 2p1s. Okay. Now, similarly, if we try to connect two of them in series, so we have got two series, 2p. That is two series, two parallel combination. So this is a whole battery pack combination, and that's how you design the whole battery pack. That's about the design battery pack. Yeah. So there are individual cells that you get. You connect. You take them into this, and then keep it in a housing. Okay. So now, how do we design a battery pack? So this is a very interesting process. So what happens is when you purchase a very large volume of cells that I've shown you earlier, let's suppose it's 650 and 3.7 and 2.6 cells, right? So when you buy these cells, you are given a data sheet in which these electrical parameters are there, and in which a specific parameter is given, that is the internal impedance or an internal resistance of that cell. Now that internal resistance parameter is being used to sort those cells. So let's suppose if there is a cell of 18650 and you are sorting it together. Okay. So when in few data sets it will be given like the internal resistance is around 180 milliohms. Okay. So any cells around 180 milliohm, depending upon the OEMs, what you can say, the plus or minus error that they give for their own purpose of building the battery pack. So let's suppose if they allowed up to 184 millivolts, and for the down, if they allowed for 178 milliohms, so that's the range that this cell can have for the internal resistance. So these cells are sorted into one place, and then they are sent for module assembly. What is module assembly? The thing that we have done just now, as you can see, this is a small module assembly. You are taking all these cells and keeping it in a series parallel combination. Okay. Now, once that thing is done, now this is the complete model that has been made, right? Once that pack has been assembled, now once you assemble them all together, then this becomes a whole battery pack. Okay. Now these packs After these are not called packs. Before this is just a module. Once a BMS is attached onto it, then it is called as a pack. Now that pack assembly has been done. Okay, what is a BMS? All those things would be explained to you later on. All the basic terminologies when you're building a battery pack would be explained to you later. Okay, and then once this BMS is attached to the whole pack, now we'll move on to the testing of it. Then it is being tested according to their own what you can say SOPs that are being defined by the OEMs. In most of the cases, the FIFO is being used, whatever first comes and that is being first out. Okay, and always most of the OEMs are keeping whenever they're storing the battery pack, they'll keep the battery pack around the SOC of 47 to 52 volts. Majorly of them, the rule book says that should be always stored in 50% SOC so that they can have a longer run life. So this is the basic diagram flow for the how the battery pack is being designed. So let's suppose if this is a battery pack manufacturing assembly. The cell comes, the cell division is done, and then what you can say, there are two things that are being attached together, the anode and the cathode, and all those things are done from the cell manufacturer's end, and the cell has been sent to the manufacturer. Okay, then the cell sorting that I've explained to you earlier also is being done, and then this whole thing is uh, bracket mounted onto the battery pack, and the module has been done. And then this is called there's something called as CCD. So there are cameras installed in a machine where it checks for the terminals that are there on the battery pack, whether they are on the same place or not. After that, the battery welding is done. Then after that, the welding that they have done is being checked properly, whether it is being done properly or not. Okay. Once that is done, then they'll check for the BMS, whether the BMS is working properly or not. Okay, and then it is being sent for the wire welding. The BMS directly connected to the battery is not welded before. Once the testing is done, then it is being welded, and then the complete battery pack is being charged and discharged once, so that the connection is completed. Once that is done, then they use a PVC film to insulate the battery pack, and once that is done, then it is being stored for shipment and all that. Labeling and packaging is depending upon the what kind of cells, what kind of form factor of the battery pack is being done. Now, next is the how the battery pack has been manufactured. So this is beyond the cell, how the cell is being manufactured. So there are two different chemistries. They are being mixed and dispersed, and then there is a coating and drying process done, and then those things are what you can say sandwiched together. Okay, and then the label for the anode and cathode has been done. So this is tab building. So basically, this is defining your positive and negative what you can say terminals, right? So this is the cell assembly, electrode manufacturing, and then once the cell is assembled, then it is inserted into a housing. And then once that is done, we have to make sure that whenever we are doing the process of manufacturing, there should be constant temperature, moisture maintained during the whole process, because that will indirectly affect the internal resistance or the electrical parameters of the battery pack. Okay, once that is done, the cell is ready. So that is about the cell manufacturing. Okay, so in summary, what we have learned till now is the first step is the cell is being manufactured using raw materials. Once that is done, then the cell is sent for production. The form factor has been sent. So let's suppose this form factor is 18650 that we have seen for the Samsung. That is being sent to the OEMs for battery pack. Then the module is produced, the pack is assembled with the BMS, and then it is being sent for the application that they are required for. Then let's suppose if it's for an EV, so then it will be integrated with an EV. And once, let's suppose the life of an EV is around 7 to 10 years, depending upon the pack size. So after that, the pack is discarded and sent for black mass. And then again, this whole process, whatever the useful black mass would be used again as a raw material to build new cells and then the whole battery pack module. Yeah. So what are the things that you have to remember whenever you're going to buy a battery pack? Always ask for what is the battery warranty. Okay, what is the dimension? So what do you mean by a battery dimension? Like if you are using it for your electric two-wheeler application, so what is the housing that you have selected in your electric vehicle to store the battery pack in? What is the chemistry that they are offering? What is the company of the cell? So is it of BAC? Is it of Samsung? Is it of Panasonic? How many number of cycles the number of cycle does that cell offer? Okay, so what is the exact battery voltage? So these are the electrical parameters that you need to know. What is the certification that on compliances that are being followed making that cell or the battery pack? What is the rating for the battery casing? In most of the cases, let's suppose if a battery is being drowned, whether it is IP rated or not, is it dust protected or not, is it waterproof or not? All those things you have to ask. Now, once you buy it, what are the service and replacement policies for the OEMs or the dealer that are providing us to the battery to us for the battery pack? Now, once you have, as we are talking about lithium-ion battery, most of the application that is around is for EVs. So there are three types of EVs that are available in the market. So there is a hybrid EV, there is a plug-in hybrid EV, and there is a battery electric vehicle. So what is a hybrid EV? So basics about hybrid EV is both the gas and the battery is being used to use as a fuel to give the motion to the EV, right? For PHEV, that is a plug-in hybrid EV. So initially for starting the car, sorry for the I'm sorry, I just okay, sorry. So I just misspoke something. So for in hybrid EV, most of the starting process to start the car is being done by battery. Okay, and then later on it is the car is moving on gas. But for in plug-in hybrid EV, the battery is being used for the long run, but for starting period, the gas is being used. Okay. Whereas in the battery electric vehicle, always the vehicle is running on electric. So it's 100% electric based electric vehicle, right? So now, as you might have heard, there is a new chemistry that is in town, that is the sodium ion chemistry, right? So this is a small comparison between the lithium ion and sodium ion the chemistry. So lithium ion is of course higher and sodium ion is quite lower at cost, but the density that the lithium ion offer is quite higher as compared to sodium ion. As of now, we know that the sodium is already abundant material, and lithium comes under the rarest of earth material. And it's that the abundance is always allowing it to be a better choice for some application. Right now, it's in a testing and research phase. People are trying to understand like how the for the anything that is built for a lithium chemistry can be used for a sodium chemistry. So they are using a different kind of a form factor to make sure that you get an equivalent performance out of that application for lithium ion that you'll get in a sodium ion. Okay. And then there was briefly around 2017, 18, 19, there was a talk about BYD batteries. So these are the batteries that were a game changer and were being used by Tesla. So why they were being used by Tesla? Because they were easily offering a better thermal conduction out of their battery pack. Then it had got a lower chance of getting the battery pack to the thermal runaway condition, since whenever they were being used for testing thermal runaways, they were not releasing any kind of an oxygen. Okay, and it was offering the similar kind of a what you can say a performance that the sodium ion were sorry lithium ion were offering, but with a better cyclicity as compared to lithium ion. So these were the tests conducted in which the NMC battery was given to a thermal condition, and in the LFP battery they were given to a thermal condition. In all the conditions, you can see that whenever NMC, since it has got a smaller energy stored in a smaller pack, it will have a huge fire and a smoke kind of a thing. But for LFP, since the energy density is quite low as compared to NMC, so it will just have smoke. Even though that is also hazardous, it's never ever been said to ever whenever some kind of a smoke comes out of any kind of a lithium ion, it is always said to keep your nose away from those things. And in the LFP, there was no smoke; there was just a small gas release. That's it. Now, now the basic so the biggest risk that the human extinction has, or the doomsday clock, is always a fire. The first invention ever done by human was fire. So the first invention when we have studied in the nurseries that whenever you try to take two rocks and bring them together, you get fire out of it. So it was the earliest invention by the early humans. So similarly, the fire was also part of the chemistry, you can say. So the biggest problem that EV right now has is thermal runaway problem, or the fire problem that comes out of it. It can be because of manufacturing, it can be because of mishandling, it can be, I mean, the cause, the deeper we go, there are multiple causes that can lead to it. Yeah. Lithium batteries, as of now, is at rise because it has got, as compared to any other chemistry, it has got lowest self-discharge rate, and the prices over the year is getting dropped. So the adoption towards lithium for the EV application is increasing right now. Okay. Now coming to the problems that it has got, even though it has got so many good things in it, but as I've told you, fire is the biggest problem that the lithium ion chemistry has got. Okay, it needs an external monitoring. So because every time you make a battery pack, you have to add a BMS to make sure that the cell is not being overcharged or cell is not being over discharged. Still, right now, again, even if the price is dropping, the overall battery pack is quite expensive, and technology to match that kind of demand to the chemistry is still in a very nascent stage. We cannot say that it is like the way it is for lead acid. It is not similar to that for the lithium ion battery pack. Now, these are the small incidents that are being happening around us related to EV fires. Now, this is just the overall view for the lithium chemistry. So, again, you can see that if you take an example, the safest battery, then the LTO comes into picture. But what is the best combination for it? Then it will always LFP, which will offer a good specific power and good specific energy density, but with a good amount of safety as well, right? So what are the real problems that are associated with lithium ion battery packs when you talk about it? So there is a chance of internal short circuit. So what happens is, as you have seen in the earlier slide as well, there are two anode and cathode, and it is being separated by a separator. Now, and whenever the anode or the cathode has got a small short circuit in between the anode or cathode, it can be because of the chemistry, it can be because of some malfunction between during the design itself. So that can lead to an internal short circuit. External short circuit, whenever the battery pack outer terminal gets shorted with either with each other or some external source, there are chances of it getting external short circuited. Overcharging and over discharging is the most common problem faced by lithium ion battery, because uh, the way we charge our mobile phones, we are charging our EVs. So that leads to a very poor usage for the battery pack and then causing thermal runaways. Of course, lithium chemistry is highly prone to high temperature. Whenever it goes for a high temperature, either it reduces its performance or it will be having a small blast or a blast kind of a thing or smoke coming out of it. Mechanical abuse is always there. Whenever an EV is being prepared, there is a specific test that is being done that is called as a vibration test to make sure that all those cells that are connected with a nickel strip are not falling apart. That can also cause a thermal runaway or a hazardous condition for the battery pack. Now, how do we tackle these problems? So we need to define some design methods. We need to have some quality things that need to be in place so that these kind of a problems doesn't go out of proportion. Okay, and the next thing is the lack of knowledge. I have seen people, and when we were building our product EV Doctor, we have seen people testing their battery packs with their bare hands, touching that, and they were having this hypothesis that whenever the battery pack is getting hot, then the battery pack is bad, and if it is working in normal condition, it will not get hot. And that was the conclusion at that point of time. This is around like 2015, 2016, the earlier adoption time, right? So this lack of knowledge gives a market an opportunity to train people about what lithium ion battery is, how do we handle them, how do we repair them. Till now, few people still think that the battery packs are not repairable. They are repairable, but up to an extent. Now, what is that extent we need to define, and this knowledge can help us to bridge that gap, right? Keeping the most of the lithium chemistry challenges are about extreme conditions. So, if you take an example of North America, where the temperatures are at very extremes. So you can get around minus 14, 15 degrees, and in a hot summer, it will go around 40 to 50 degrees. Then at that point of time, how the chemistry would behave or the battery pack would behave, these are the extreme conditions that the battery needs to prepare for, right? Now, these are some stats of EV fires, and as you can see, most of the EVs that were parked, in most of the conditions, the parked ones were always charging, right? Most of the cases, they left their vehicle overnight to charge, and then it's in park condition, and that led to a thermal runaway. Yeah. So these are the stages where how lithium ion thermal runaway happens. So as I've told you that there are anode and cathode. In between, there is a small separator or a liquid electrolyte. So whenever lithium dendrite or a separator flaws, these are manufacturing defects. Lithium dendrite always forms whenever you are using your battery pack, right? But it happens to some extent. If it goes beyond some extent, then it will have a problem. Okay. Now overcharging can be a problem, and can get crushed, which could lead to a higher current, right? So that would have a problem with this. Okay. Hello? Am I audible?
Yes, you.
Yes.
Yeah. Okay.
Yes,
Okay. Sorry.
audible, sir. Audible. Audible.
Actually, somebody's writing that I'm not audible. Okay. Fine. Okay. So, and yeah, so I was talking about the thermal runaway conditions, right? So these are the steps that happens, and let me tell you that I've seen those things happening in front of my eyes when we were preparing for the hardware for the EV doctor. We have seen that within few seconds, the smallest of the smallest cell you take, it will catch fire, right? So it is always required to understand that even though these stages are written in words, but they take few milliseconds in which they can get fire. And liquid is not the solution to it. If you put liquid into it, it will catch more fire because it releases oxygen. Then that's a cascadic reaction happens. So we have done that also. We know that it is not good for it. I won't suggest it to you for happening. Have a proper, fire extinguisher thing with you to make sure that you. And there are different separate kind of fire extinguisher as well for just for the lithium-ion battery pack. So this is the small image that we have taken. Where we have mounted we have taken a brand new battery pack which is equipped with different sensors in there, right? And then what we have done is we have deliberately put it into thermal runaway condition. And initially we were taking the data to understand like how the electrical parameters related to the battery packs were changing when they were getting into the condition. And at that point of time, we were also noting what kind of temperatures it was reaching, right? Now, this is the temperature characteristics that we have seen. So as you can see here, at this 13.80, you can say around 9, it reached black smoke, and within few seconds only it reached to the large flame. Okay, and it caught fire instantly. And there was no reaction time as well. So Aditi, I'll take the questions after I think after the session, in the Q&A session, I'll take all those questions. You can write down all your questions. Okay. Fine. Yeah. So these are the parameters that we got when we were doing the testing at the IIT Gandhinagar. We were given a specific spot to test 40 plus battery packs of different kind of battery. We made a specific battery module. This kind of specification you don't get 48.6 volt in the market, right? We made a battery pack. We tested it. We were using old battery packs. We were using new battery packs. We were using older cells and all kind of chemistry that was there. 40 plus combinations were used to understand how the temperature behaves. In that case, also we were testing whether the BMS were able to react to it. If you can see closely in here, so when the thermal runaway condition was happening, BMS did try to disconnect the battery pack and again connect it to make sure that this is not a false condition. So those behaviors were also being captured at that during that point of time, right? So it was not a custom BMS. We were using a normal BMS that was available to everyone, so that to understand like how the BMS behavior is there, which later on helped us to understand BMS better. Okay. So now we'll start with the diagnosing of batteries. So how do we start the diagnosis? So first you visually inspect like what is happening, if there is any physical damage to the battery pack. Are there any leaks? Since it's a chemistry kind of a thing, right? So there might be leaks, there might be dents, there are some loose connection. Most of the problems, when you see it from your bare naked eyes, you can see that there might be chances that the connector to the BMS might be loose, or the terminals coming out of the battery pack might be loose. That might be causing some kind of a problem there. Okay. Next is we test the battery pack. It doesn't matter if you take EV or any kind of a machine that can help you understand the battery pack. You need to understand like what is the problem happening, and it is always recommended that like every 6 month or 8 month you get a battery at least tested to know that whether the performance that I want out of the battery pack is coming out or not, right? So the parameters that we are looking for when we are testing a battery pack is like what is the capacity that I'm getting, what is the health of the battery pack, what kind of faults that are is there any kind of fault that is happening inside the battery pack because of which I'm not able to get the performance that I should be getting. Okay, so these are things that we look into when we are testing a battery pack. Now with the basic things like we can check with the string voltage, you can use any kind of a multimeter to just check whether you're getting any string voltages or not there. Next is balancing the cell. See, as you have seen that we take small cells and keep it in a module, in a series parallel combination. Each and individual cell have their own voltages, right? Once you start using those cells, we have to maintain those cells on a single voltage level. So there is upper cutoff and lower cutoff of the cells when we make it, and allowable limit to it. Like let's suppose if a cell in a battery pack is given a 3.7 volt nominal voltage, and around the pack when it is being made, it will have some 3.65 because there is a circulating current flowing in between those cells in the series string or the parallel string. If the battery pack and the BMS is allowing that much amount of the design of BMS is allowing that much amount of balancing current to flow, then it is fine. If it is going beyond that, you might not get the performance that you need to have from the battery pack. So that's why the balancing of cell is always required. Whether you're making a battery pack, whether you're repairing a battery pack, whenever you're opening the battery pack, make sure to balance the cells. And how do we know whether we need to balance the cell? We need to check the string voltage that I've told you earlier as well. You check the string voltages whether they are the same or not. Yeah. Then again, when you have completely checked the series string and all those things, then after the pack is completed, you check it whenever whichever way you want. You can check it with your doctor. You have got different machines for it to check. Now, these are the potential problems that we have seen till now with the electric mobilities around the globe, right? So the quality is a big concern because the kind of lithium that is being floated around the world is not of a good quality. The higher qualities are being either sold in a better models or not. And the similar thing is happening onto the service side as well. The service to for the problems that are there is not proper because of the we can say value chain is not completed. The parts are not available, and these causes some fire. And since it's a lithium ion has got a potential inherent risk of battery fires as well. So if there are measures that are there to prevent those things, those are very less. Okay, and still now, if we buy a new electric vehicle and if I want to sell it again, there is no resale value that we can have right now to understand what the exact value for is. If you buy an Activa for let's suppose 1.2 lakh or 1.3 lakhs, depending upon the state, you can have around 60 to 70,000. Even if you sell it in any other state, minimum that you can get. But what is that exact resale value for any EV? You won't have a proper value to it. And the reason behind all those things is the all over the wherever you go for testing or wherever you go to build those things around it, the complete process is slow. We have seen multiple service stations that are having bigger machines, but when we ask them like how much time does it take for you to, or how many backlog do you have, so they have got hundreds and thousands of backlogs with them, right? So it's not their fault because the whole SOP is around built around some old machines that are not intelligent inherently, right? So even though they'll give you some amount of insights, but that won't be enough for you to understand what exactly the problem is. It will give you a specific things only that won't be useful for you to take a decision, right? So commercially, we install CDC machine at least 6 7 hours to just test the whole thing, the whole battery pack, right? And it is very complex to use. It is not that easy to use, and that's what it's very bulky. I've seen big bulky machines that are there, and it gives you very limited insights out of the machine, right? You get either the voltage and the capacity out of. Sorry. So this is just about our machine that we have built. It's called as an EV doctor. What has happened is those tests that we have done with the IIT Gandhinagar, we have taken data from NASA. We have taken that are available around the globe to get real-time data sets to train our AI models to understand the batteries that are there. So essentially, what EV doctor does is they take the real-time electrical parameters during the charging itself, feed it to our AI ML platform that understands the current condition of the battery pack and give insights about the health, safety, and the faults that might be inside the battery pack. Those faults are all are covering the most common faults that you see because we have talked to 1500 plus EV dealers, EV workshops to understand what are the problems that they get when they are having battery pack or the EVs with them for during the service, what are the problem and the things that they're having, or as point of the battery pack manufacturer or EV manufacturer or anyone who is associated with battery pack, what are the kind of problems, and then we have briefed those faults or the problems and converted it into a very easy, understandable report format where anyone can understand and take a decision out of it. So as I'm just a brief about it, it takes almost, I mean, half the time or less than half the time to get you the diagnosis for the battery pack. We have got integrated 20 plus algorithm, and still we are integrating more algorithm as and when we are learning more about battery packs, we are able to understand that the kind of data we have is more than enough, but still not enough to give you the best result out of it. Why? Because batteries inherently are like humans, and every human is different, right? So every time we go and chase for a new battery pack, we see there is slightly something different about this battery pack. We learn about it. We integrate all those things into a battery pack. Every test that the EV doctor does or any client of EV doctor does, those data is being sent again to the AI platform to learn about that battery pack as well. So basically, what we do is the principle behind EV Doctor is it works on a principle of DCI and voltage current profiling. So DCI, let me give you a brief about it. Most of the testers that you'll get in the market will work upon ACIR, so that's an alternating current internal resistance, and we are working on upon a principle called as DCI, that is direct current internal resistance. So what happens in ACIR? Most of the testers, they'll send a 1 kilohertz signal to the battery pack and receive a response from the battery pack, and according to that, they take a decision of the what is the IR value for it. There is a table for it that you can refer to, and then you can get to the value. But whereas in DCI, what we do is we take V and I ratio per second, and then we take those values into picture every second how the DCI values are changing. And similarly, we are comparing the voltage profile and the current profile during the charging itself. And these all parameters are being sent to the MLAI platforms where we are trying to understand what is currently happening with the battery pack, whether it is and whether it is having some kind of a fault inside it, whether the battery is healthy or not, does it have any safety concern regarding that or not. And these battery packs are being compared with 2.5 million data sets of varying kind of a battery packs. So be it a older battery pack, a newer battery pack, a battery pack that was used for 2 years, and then according to that, those conclusions are being fed to the app, and health, safety, and fault report is generated inside the phone itself, which will be stored in your phone. Whenever you want to check it, you can check it at any point of a time. So this is just whatever I've said. This is just a brief about it. We have used the XGBoost, XCalman, K-means, all these algorithms. Since these algorithms are for general purpose only, we had to modify our algorithm to act to be used for us for our specific application to understand how the battery behaves. We have to teach them what is CCC, what is the charging curve, what is the cell parameters, all those things we have taught to the algorithms, and we have modified it to use for our usage to understand what is fault, what is health, and then it is able to understand how the battery is behaving and then make a conclusion out of it. Right. So since right now 2.5 million data sets are being used, we are getting approximately 97.3 accuracy all over the battery packs right now, and it has been training on different chemistries, be it lithium ion, be it sodium ion. Sodium ion is not there as of now for the data sets, but we have got cell data sets, and we are still building it. There are a few things that are there again in the pipeline as well. We are building BMS that would work with the AI to have a better kind of a quality out of the battery pack. So these are our R&D things that are happening around this tech. So this is the how the the EV Doctor works. It gets connected between the battery and the charger. It is using a normal Type C kind of a mobile charger to switch on the device and give you a result out like this. I'll later on after this call, I'll show you a demo how it is being used and how this report is being generated. So basically, what happens? The device over the Bluetooth protocol talks to the Android app, and Android app is connected via the internet to the cloud platform, and where all the computation is done. So basic parameters like voltage, current, what is the behavior of the voltage and current, the profiling, and the DCI that we are getting are being fed to the cloud. And in calculation of it, we are getting the health, safety, faults, what are the energy level. It also provides you AI tips that like how to use the battery pack, why it is a good battery pack. Those are things are being generated directly by the AI itself, and the faults that are very common occurring on the ground level are being covered in this. Right. So we have made this a universal kind of a thing where it can be used. It's the size of a palm. You can take it anywhere and you can test it. You can take it to the customer and you can take it at your home and you can test your own EV battery with it. All those things would be useful for you, right? So the ideal way is you save up time. You diagnose the battery pack in a very smaller time, and you get the output of it, and you can take a quick decision what to do with the battery pack. So this is just the comparison between the things that are available right now and how EV Doctor is better. So the major thing that we have done with the ML algorithm is that we have taken all those data set to take a decision within 15 minutes by the EV Doctor using all those data that are there, and those data are still being trained again and again to make sure that we maintain that accuracy that is there, right? So this is just about the market. We'll move on to the yeah. So now we'll go to the battery and battery terminologies that are there. So whenever you go buy a battery pack, so these are the terminologies that you need to know. Earlier I have discussed few things. Now there are more things that are out there. So whenever you go buy a battery pack, there would be a spec sticker in which that spec sticker or in the data sheet it would be defined that what is the nominal voltage, how much is the ampere hour, what is the no load terminal voltage when there is no load is connected, what's the voltage that you get on the terminals of the battery pack. That is sometimes called as open circuit voltage, right? And what is the charging voltage of the battery pack at what, that means what at what point of time I can say that the battery pack is fully charged. That is been defined in the spec sticker, right? What is the minimum cutoff? This is not defined in every battery spec, but it is given in the data sheets that how much is the lower cutoff or the discharge cutoff of the battery pack. What is the battery energy? So how much kilowatt hour this battery pack is. So these are some basic terminologies that they are there. So now we'll have some small introduction about the service and repair. Okay. So these are the basic tools that we suggest you should have. So like to open the battery pack, screws and all, then for charge for repairing, you need to have solder and all, battery testing kit of EV Doctor if it is, or maybe some other machines you can have. Now motor control test is there where you can in that motor control you can check each and individual problem if there is a Hall effect problem or some other kind of a problem with the motor happening. These are things are detected in the motor control testing kits. Yeah. So introduction to EV. So EVs are basically that are being powered by electric motors and traditionally being powered by a battery as compared to the petrol or diesel engines, right? Next. So this is the just basics of EV. What is inside of EV? So there would be a charger, there would be a battery, and there would be a motor. And this motor is called as control and mechanic power generation, and the electric energy storage, and there would be a charger for it, right? So this is how it would look into inside a electric vehicle. So there would be a motor, there would be a battery pack. For protecting the battery pack, there would be an MCB that would be connected between the battery and the charger and the motor in the battery, right? And there would be a junction box. There would be a controller to control the motor, and all those things would be there. So this is again just a like quick overview about what you get inside a EV. This is for the electric three-wheeler. You have similar kind of a thing, but on a bigger, larger scale because the battery pack there is of hundreds of volts, 120 volts, 130 volts, something kind of that. So if we break down for any EV, there would be two parts. There would be electrical and there will be mechanical. Electrical will have battery, charger, motor control, DC-DC converters, wire harness, speedometer, whereas in the mechanical side, the chassis would be there, the brakes would be there, wheels, suspension, plastic parts that are there. So these would be considered under the mechanical part of the vehicle. So this is the two views that you get on the left hand side, on the right hand side. These are the things that are there, brakes, all those things. So these all things I will not go through because you'll get this document. You can go through it. If you have got any specific questions regarding them, then you can send it to me after the session as well, or maybe later on whenever you go through it, you can send it to me on the email. Yeah, this is the basic subsystem you get in the electric vehicle. So there is this battery pack. As I've told you, between the battery pack and the controller, there would be an MCB to protect the battery pack so that not a large amount of current is being drawn by the motor. That is being made sure by the controller. Even if it goes beyond that, then the MCB gets stripped. Okay, and there is a charger in between. When you have to charge it, there's a motor controller is directly connected with the odometer of the battery of the EV. Okay, next is, yeah, electrical parameters. I already mentioned about it: voltage, current, electrical power, electrical energy. So these are the basic calculations that are there. So when you talk about watt, so watt means voltage multiplied by amps. So these are some basic things that you can go through later on. It's just basic electrical things that will help you understand what how does kilowatt hour comes into picture. When you go and buy a battery pack, they'll always talk in terms of how much kilowatt hour battery pack it is, right? So how do we calculate the kilowatt hour? So to convert that, so let's suppose if you've got a battery pack of 48 volt and 10 Ah. So you will have something as 720 watt hour battery pack there, right? So instead of 10, because this is we are calculating the electrical watt, right? But if you take the nominal voltage and the current that is the capacity that the battery pack is designed for, and you take the product of it, you'll get the kilowatt hour out of it. So that's how you calculate. So it's like a simple basic terms that you need to understand. Yeah. So whenever you're at a workshop, you need to have a multimeter to have a basic idea about what is the voltage, whether there is a continuity failure or not. Okay. How do we use a multimeter? This is some basic things that is being given in this document. Where how do you measure a AC voltage? How do you measure a DC voltage? So for the AC DC applications, sometimes when you're making a DC, there are the terminals that you're connecting with the battery pack with the BMS. Sometimes the terminals are opposite. How do you identify that? You keep the multimeter in a DC position, and then you try to see what is the voltage that you're getting. If the voltage is negative, that means the terminals that you have connected is in opposite direction. You have to change those terminals. So these are the basic things and basic knowledge you need to have when you're operating a lithium ion or a EV battery pack. So this the thing that I've told you right now, it's called as polarity, right? If you don't follow the polarity, so to understand what polarity is, so the positive should be connected to the positive end, and the negative should be connected to the negative end. So that's a basic about it, right? If it is not that, then it would be a hazardous condition for the EV, right? So we need to understand about polarity as well. So these are some basic terminologies that you get, right? They see what I've told you earlier as well. So how do we calculate the kilowatt hour that you'll get out of the battery? So if it's a 48 volt battery pack and it's a 28 capacity, design capacity of it, so the watt hour you'll get approximately is a 1.3 kilowatt hour if you divide it by 1000, right? Similarly, for a 72 volt battery pack, if the capacity is 28 you'll get around 1800 watt hour battery. So this is how the energy is being calculated, right? Types of battery that you get in the market. So this is again about LFP, NMC, LMNO, lead acid, the two things of the type of batteries that you get during the servicing as well. As you know that if you compare lithium ion with lead acid, lithium ion has got a smaller charging times. It has got a better discharging curve. It has got a what you can say better battery life as compared to lead acid. And most and foremost, the calendar life of lithium ion is way much more higher as compared to lead acid one. Or any kind of a battery, do not open the battery pack, never puncture the battery pack, and always avoid overcharging. It is not good for the health of the battery and as well as your own health and safety. These are the things that you have to keep in mind when you're using or operating a battery pack. It is always like good habit to charge a battery between 20 and 80. The rules of 20 and 80 is being followed worldwide, where to make sure that you get a longer lifespan. It doesn't matter if you've got NMC or LFP. Whenever a customer is coming and asking about electric vehicle, we often tell them to always tell this to the customer so that this headache doesn't come to you, because customer doesn't understand between the charging and discharging, right? They use EV like their mobile phones. They charge it at 50%, they charge it at 80% because they like their battery to be at 100% always ready for them to go, right? Because the charging time for lithium ion is always greater. But keeping that in mind, we need to help them understand that 2080 is good for their um, 2080 is good proportion for them to have this, right? Now coming to the battery specification and on any kind of a battery, as I've told you earlier as well, nominal voltage would be defined. What is the charge cutoff voltage? What is the floating voltage? Floating voltage is always available on the lead acid. It is not available onto the lithium ion because it doesn't have any self discharge and kind of a thing. What is the charge and discharge cutoff for the battery pack, and how much is the charge used for the battery pack to charge, right? And what is the maximum charging current out of it? All these things are there. Yeah, this is just the brief about how EV battery diagnostic points are there for manufacturing, from manufacturing to recycling. As I've already told you earlier as well, this is how the whole cycle is, right? So how does EV Doctor help you whenever you are buying an electric vehicle? You test it. Whenever you're selling it, you're testing it to know the capacity, health, and any kind of fault is there or not. To give it a, what kind of kilowatt hour to rupees ratio is there. So there, so that you can sell your EV to at a bigger price point, or a price point that is suitable for both the parties. And it is definitely helpful for you to repair whenever there is a problem with the battery pack. To understand how to diagnose the battery pack, we need to understand what are the tools that are available, what are the faster tools that can help us give a better kind of a service to the users. So that is where the EV Doctor comes into picture. So this is how the EV Doctor is connected. So one end is connected to the battery, other end is connected to the charger, and it is using a small, any normal Type C cable mobile adapter to just charge it. And you can see it's a small size device which can identify any kind of a problem in the battery pack. This is again the report that you get. These were the earlier days when we were pitching to dealers and distributors to understand what battery, what you can say, how does EV Doctor work, how it will be helpful for them. We were delivering initial days of our delivering and making them understand. So now we'll start with the basics about the battery pack. So what is an BMS? So as I've told you, to get the just a second. Yeah. Hello. Yeah. So to make sure that the cycles that you want out of your battery, it should be the performance that you want to get out of your battery. To make sure that the battery pack is safe, it is all being managed by the BMS system, right? So be it to maintain the cutoff voltages, be it to maintain the current that the battery pack should give out during charging or discharging, both the things are being managed by battery BMS. So essentially, it is the brain of the battery pack, right? To make sure the battery pack is safe, it is under the thermal limit that are there, and it is always continuously monitoring the electrical parameters of the battery pack. The cells are within the well within the limits. Whether the current that is coming out of the MOSFET is well within the limits. If there are chances that this battery is going beyond its limits, it disconnects the battery pack from the BMS so that there is no terminal voltage out of it. So these are the things that are BMS is taking care of. So this is the whole, how does the actually battery BMS works? Is the whole overall picture of it. So these are the cells that are connected. Now there are different sensors that are connected inside the battery pack depending upon the design of the battery pack. Few people have few thermal sensors connected into it. There is a shunt connector or a Hall effect sensor inside a BMS, and these parameters are being fed to the BMS, right? And when this measurement is done, the conclusion related to their capacity, the state of charge, the state of health or thermal, whatever the temperature is there, are being sent either by the CAN bus, or if there is a display, it would be shown onto the display, right? So this is the basic architecture of the BMS, where it takes the voltage, current, and temperature. In most of the cases, you will get the current and voltage in the earlier versions of the BMS. Now later on, people have started integrating temperature communication pins display onto the battery pack so that they can understand like what is the current condition or what is the SOC right now with the battery pack. And there is a for the communication, Bluetooth is there, Wi-Fi is there. Sometimes in some cases with the BMS, there are SIM modules integrated with the BMS so that you can monitor from anywhere on the planet on a dashboard where you can see like what is the temperature, what is the voltage, what is the current, what is the status of the battery pack right now. So how does it actually work? So basically, what happens is the BMS is connected via different sensors in there, and those sensors are taking those thing into picture and giving either onto the dashboard or to the user that what is the health of the battery, what is the safety of the battery, or maybe the rules are defined differently for BMS architecture that is there. So according to that, they are giving the output onto the screen or onto the app, or whatever kind of an output is given onto the display, right? So this is the whenever there is a cell, and in the cell, whenever the data sheet is given to the client, so they are always defining what is the peak charging current and peak discharging current for a specific lithium chemistry, right? So here it is just the overall view. Like if you've got a lithium chemistry, the continuous discharging current that you can take out of is either only -8 amperes. You cannot go beyond. If you go beyond that, then there are chances that it can lead to a safety problem. It can damage the cell itself, right? The performance that you're getting in the first cycle, you won't get into the second cycle. These are leading to performance degradation and indirectly to the hazardous condition, right? On the charging side as well, it is perfectly defined, right? So now what happens is the cell manufacturer have their own data sheets, and according to those data sheets, the battery pack OEMs are manufacturing their own battery pack, and then they are giving their own data sheets in which they are defining that these cells are being used and these are the limits that are being allowed to operate the cell within this condition, right? And most of the cells are always operating between 4 and 2.5 volts in case of a lithium, right? Similarly, for the temperature itself, it is also defining like less than -20 degree. If you go, you'll have discharging within few minutes, and if you go beyond that, then this could lead to a thermal runaway chances if you go beyond 60 degrees centigrade, right? For in case of discharging, whereas in charging, there would be the temperature allowable limit is around 30, 35, 38 degrees centigrade, right? If you go beyond that, then that would lead to a very hazardous condition. Now, the thing that I was talking about is balancing of cells. Now, in this, you can see that these cells are connected in series parallel combination, right? So each string, let's suppose if this is not a cell, it's a string, though, you are getting a 3.2 volts. When these volts are on the same voltage level, so there would be a limit to it. So few OEMs follow like they will allow up to 3.25, we may allow 3.15. So overall, there would be a limit to it, and all those limits are of the same value. So let's suppose if this is 3.2, all the cells are in the same value, then the pack is called balanced pack. If when either by manufacturing defect or by using when you're using the cells, these cells degrade according to their usage or the chemistry defined by the manufacturer, right? So if we are not following those rules, there are chances that internal resistance of us, let's suppose in this case the cell 5 is high, cell 4 is not that much high, but in the similar case of 3.3 volts as well, right? So these cells will have their own what you can say internal resistance and causing them to have a circulating current flowing in between them, right? And this will make the balanced pack unbalanced, right? So let's suppose if the battery pack was able to give you 20 volt, it won't give you 20 volt. It will charge up to let's suppose 18.8 volt because one of the strings has reached to the upper cutoff voltage. So the BMS will think that the cell has reached because all these are connected in series, right? So whenever the one of the string has reached to the upper cutoff voltage, then the charger would cut off because the BMS has given signal to the charger that the battery pack has completely, charged. But in actual fact, all these cells were already not to the peak, but just one string has reached to it, and that's why the pack has reached only to 18.8 volts, right? So this is the BMS topology. What happens? So different BMS architectures are there. So there would be a central BMS which would connect with each and individual strings. So they will talk to each other and then give information like voltage, temperature, and all those will be central BMS. There is one more architecture called as two module BMS in which there will be two separate BMSs for a bigger, larger battery pack. For let's suppose for a case of a truck or maybe a case of a trailer, they'll have two different BMSs that will be talking to each other to tell that these strings are having this much voltage and they'll be communicating with each other, right? Now, there is one more architecture. This is a master slave in which there would be a main master BMS which will be monitoring all the data sets that is being given to the secondary BMSs and would take appropriate decision for that. And then there is final distributed. This would be a quite this would be quite uh, hardware intensive BMS where each and individual cell module is given a BMS where the voltage, current, and sensor output is given to a single controller, and that controller takes the decision for each and individual cell module. Now, how the sensing is done, as I've told you, we use resistive shunt based or Hall effect based sensor to sense how much current is flowing inside the BMS. Voltage is being taken by ADC based temperature. There are thermistors, thermocouples being used either onto the BMS or separate connectors are given for it. Yeah, this is about the control. Okay. So these are some basic ideas. Okay. I'll not go through them each and everything right now because we have got a lot of more slides to cover up right now. Okay. Next is the estimation technique. So what happens is whenever BMS is there, there would be algorithm firmware algorithms running to take the voltages, the current, and temperature into picture to take an appropriate decision like what is the state of charge of battery pack right now. Okay. Now these things in the newer generation of BMS is being fed to a model where they are estimating the charge left inside the battery pack, what is the state of charge inside the battery pack, what is the resistance of the battery pack right now, which in turns help you understand what is the overall energy and power available at the end of the terminals, right? So that's how the estimation technique inside of BMS happens. So basically, two parameters are being used to estimate state of charge and state of health are being the parameter output that is being taken out of the battery pack via the BMS, right? This is just a brief about SOCs. What is the state of charge? So it is defined as the ratio of capacity that is there inside the battery pack right now and the designed capacity or the nominal capacity of the battery pack. This gives you a brief idea how much energy I can take out of it. So when you're charging your phone, so 90% phone is being charged when you say that means 90% capacity is available for you to discharge your phone, right? For your application, for a phone call, for watching a video, and all those things, application it is being used. So that is how you define an SOC. So there are different techniques to estimate. There's a Coulomb counting, how much is the current flowing from the battery to the load. It is being measured per second or per minute, and according to that, the SOC is being estimated. Then we use Kalman filter to estimate the SOC. These are the Kalman filters are the basic algorithms used to estimate the SOC in the earlier days. In the most of the earlier papers, you will get Kalman filters for using SOC prediction models. Now, as I've told you earlier, the BMS used to be dumb BMSs. They only used to take the data and give you an indication either on the display that this much is the SOC. Now, as we are moving ahead, the integration of balancing power, and the understanding of SOH, and all those things are being emerging out of the BMS technologies right now. So, with the IoT connection inside the BMS as well available at your fingertip, you can take those data and understand what is happening in the cells, right? So these are some basic things that we always give to our clients to understand that how do you take battery servicing and repair, and these are just small things that you have to always consider. I've already discussed this in length at earlier of the this. Now after BMS charger comes into picture, so it is always recommended that whenever you are buying a battery pack, always have the charger that is being given by the OEM. Do not buy some external charger or universal charger because the universal charger doesn't understand or is not being designed for the battery pack that you're using, right? Because the universal charger would have a different kind of a cutoff, but a specifically defined charger would have a different kind of a cutoff, right? So it will follow, it will make sure that it follows the curve that it should follow for the design battery pack and make sure you get the cycles out of the battery pack, right? So there are different indicators that you get. Different OEMs follow different kind of a thing, like how much charge is being done. So these are some basic ideas like how much is the battery is being charged. So you get 25, 50%, 75, 100%. So once you reach to 100%, the balancing current kicks in to make sure that the trickle charging doesn't happen. You reach to the exact charging voltage that the battery pack should be, right? So these are some basic ideas about like how do you use the charger when you're using the charger. Do not switch on the vehicle at that point of time. Just before that. Okay. These are the steps that you have to follow. For let us say different kind of steps are being followed for for lithium ion different kind of steps are being followed and these are being descriptive about it. So these are the charging parameters that you get when you are using a charger. Every charger that you get has got a different kind of a socket. So always make sure that you do not make your own socket and then try to connect your socket to that then because of polarity problem. you might end up having a damaged battery pack or a damaged BMS. So always, whenever you're making a charger to the, connecting a charger to the battery pack, always follow that the positive is connected to the positive and negative is connected to the negative. Because if you are connecting it into the reverse, there are chances of safety concerns. There are chances the battery pack might get affected, or there are chances that the MCB or the protection circuit that is inside the EV can get affected because of that. The next part is the motor. So these are, I'll not get into details about this as well. There are different kind of motors that are there. BLDC motors mostly being used. Yeah, I'll skip this because we have got an FAQ session as well. Motor Hall effect sensors. These are basically giving you an idea where the position of the motor is right now. And according to that, and there are testers to tell you that when you connect this tester to the motor controller, it gives you a brief idea that what is the problem. Is it because of Hall effect sensor, or some LED is having a problem, or rotation of the vehicle is having a problem, some kind of that. Okay. Controller, it gets connected with the battery and the charger, makes sure that the motor is getting enough energy or the juice to take the load and move the vehicle forward. For different controllers, for different battery, for different motors, different controllers are there. So sometimes what happens is 48 volt, or if it's a 72-volt battery pack, and the controller is of a 48-volt battery, then you need to have a DC-DC converter in between to get it to that point. And most of the LEDs or throttles or lights that are there on the EVs are working on 12 volts. So you need DC-DC converter as well for that, to convert that to that level. And 72 volts converted either to 12 volt, or it will be converted from 48 to 12 volts. That would be used to switch on the lights. Speedometers is there. This is the line diagram how the motor and battery pack is being connected with throttle and controller. So it's a very general power line diagram for the EV. Yeah, I'll move from here. Yeah. So this is whenever you find a fault on the EV, what are the remedies that you need to do in to understand where the problem lies. These are just giving a brief block diagram just about it. Okay. This will be given to you. You can go through it. You can understand. It's a very basic, simple, plain English. You can understand what to do. Okay. So I'll just give you a brief about AN batteries. So the datasets that we have taken till now are being used to understand the battery that are being floated in the market, be it sodium ion that is going to coming. We are taking those data as well to train our model, so that in future any other kind of a battery, salt battery, or any kind of a battery, or any kind of form of a battery are being used. This platform will be able to help them diagnose the battery pack. Okay. So that's why the integration of AI is very much necessary onto the diagnosis end as well, right? So I'll give you a brief about like what does AI in the concept of diagnosis happens. So what we do is in terms of our EV doctor, we take the basic as it is being connected between the battery and the charger. We are taking the basics, voltage, current, and making a DC IR and voltage current profile. And now these parameters are being fed to the model, where there are different type of classifiers. For, let's suppose it's a healthy battery, the classifier would go and create a probability whether this battery is having a good health or not, and then it is being constantly compared with other data sets as well, to give a firm decision on whether this battery that we are testing is having a good health or not. Similarly, 25 plus algorithms are being used to get the faults out of the battery pack, right? So this is just the basics about MLAI algorithms that we're using. Multiple, I mean, 25 plus algorithms, and each algorithm is having their own subset algorithms to take the data that we are getting from the device to the cloud platform, right? So AI is not just limited to diagnosis. As I've told you, BMS is getting integrated as well into it. Different algorithms. If you go to Google Scholar or any platform that is providing you the idea about energy, there are different algorithms that are being used. You might have heard about a new charging algorithm that is being developed. There's a pulse charging algorithm where it is being seen that if you use a pulse charging, there are chances that the battery pack would last longer as compared to if you normally charge it. So in the case of both charging and discharging, if you're using a pulse charging, right, pulse based, charging. So we have done, as I've told you, we have done 40 plus thermal runaway condition tests in there, which has helped us to build a model that understands the safety of a battery pack to take a decision for it, right? And it has covered many multiple types of batteries to understand the diagnosis, to give a firm decision on the type of batteries that are there. So these all things would be available to you, right? Okay, so that's about the presentation. I'll just give you a brief demo on how the EV Doctor is being used. Then we'll start with the Q&A session. I just want to have more Q&A session so that we can discuss about the things that you have understood and or is having any problem with that. Just let me know if it is this is available to you. Hello. Can anyone just confirm whether this is visible to you?
Yeah, it is visible.
Okay.
But it's not audible actually.
Okay. Just give me 2 minutes. Is it audible now? Can anybody confirm? Is it audible now?
No, not yet.
No, sir.
Okay. What I'll do is I'll just disconnect my earphones and I think it would be audible. Is it audible now? You let me know.
Yes, sir.
Yeah, now it's audible.
Okay. I'll just restart it so that everybody is able to see from the start. Okay.
Hi, myself Darshan. Today we are going to check this battery using EV Doctor device. So there is a three-step process for any battery check using EV Doctor. First step is connect the battery. Second step is to connect device. Switch on the device. Just connect EV Doctor device to EV Doctor application. We have to fill these relevant details like client name, client contact details, battery serial number, battery type, battery voltage, and battery capacity. Or we have to select flash mode or normal mode. For now, I'm going to use flash mode. This is the app interface. And now I'm going to pair EV Doctor. For first time, we have to pair like this. Doctor. And after pairing the device for first time, so here is the ID for EV Doctor device. There are warning Make sure the corrections are done properly before starting the test. I'm going to OK. Yeah. Here our device is connected, and now I am going to connect charger. Third step. The charger is connected. Okay. I am going to start the test, the flash test, and turn on the switch of charger. So here is the battery voltage. Current is 0 because yes, the current is showing up the battery SOC and battery capacity. And now we have to wait for only 15 minutes to results for this battery checking results. Okay. So whenever the test is done, I am going to show the results. Okay. So the 15 minutes is completed and we got the alarm and test completed notification. Okay. I'm going to OK. And first we have to turn off charger switch and finish the test. Okay. So here is the results. First one is battery health. Battery health is 4 out of 5. Battery health is good. Safety levels. Safety levels is high. There are battery faults. 0 battery faults detected. Battery health parameters shown in detail. Battery safety levels. And here is the step-by-step for faults details. First one is short circuit. Second one is a imbalance. Third one is a BMS fault. Fourth is a charger fault. Fifth is a deep discharge. Six is a overheating. Seven is a reverse current. 8 voltage drop problem. 9 water damage. And 10th is a aging fault. And we can share this report through client via WhatsApp, Drive, mail. You can share this report.
So this is just a brief about like how do we use the device and how do we get the result. Okay, so that's it from my end. Now we can open for Q&A. Okay, so I'll just stop sharing my screen. Yeah, if anybody has got some questions, you can share. I think Swati ji was asking for questions, something.
Hello.
Yeah, hi.
Yeah, hi, this is Swati. So I have a couple of questions. First was regarding the thermal runaway test that you showed, right? So
Yeah.
I was just wondering, so there are several ways of inducing the thermal runaway. So what major focus, like, did you use voltage? Yeah.
Okay.
exceeding-
So, I mean, we had done during the testing itself, we did thermal reviews where we have given it a like an external heating to it. So that is one of the things that we had done. We have given it a vibration where we have intentionally did a loose kind of a soldering onto the nickel strips to make sure that during the vibration the cell gets disconnected and it gets into the thermal runaway condition. And practically we have shorted two cells together and then try to take the readings out of it during the temperature itself. So there were multiple conditions that we were taking considering during that. So the idea during that was to understand how the BMS behaves, how the pack behaves, and how a cell, we have like I think 100 or 150 different types of cells that we have punctured, for like pouch cell, for lipo cells and all kind of cells, to see like what is the time duration it takes for it to catch fire or take smoke, I mean the time to take the smoke to come out and all those things. Yeah.
So basically propagation, some thermal propagation.
So when we talk about the whole battery pack, if what we have seen in our case, when a single cell, let's suppose one of the condition was a cell that was in between the battery pack, we had intentionally given it a nail puncher. Okay, so once one of the cell got into thermal runaway condition, because of the temperature variation in that particular string or module, we were able to see that 3 4 more cell adjacent to that cell got into thermal runaway, right? And that thermal propagation happened, the whole battery pack blew up within few seconds.
Mhm. Yeah. Anything, again, I know that external heating, vibration, etc., they will definitely induce thermal runaway. Any test that, that you did for, uh, usually when the battery accidents happen, right, it happens during charging
Yeah,
or,
yeah.
when the customer. So, for that, for
Okay.
simulating
Okay, I
that
now
scenario,
understand what you want to know. Okay. So in that picture, what happens? We had 10 different types of battery pack with 10 different BMSs. Where what we have done
Mhm.
intentionally, the design of a battery pack, let's suppose is 24 volts, right? And it has got some upper cutoff and lower cutoff. We have used an alternate
Yeah.
kind of on a BMS, which was for
Mhm.
I think 12 volt or a 13 volt, and we have connected that. So in that condition, what happens is has got protection circuit inside it, so it
Mhm.
is already well beyond its limit, right? And when you are trying to charge or discharge it for both the condition, within few seconds, the BMS did try to protect it, but since it's a new BMS, it is not a used BMS. It behaved the way it should behave, but the thermal runaway and the propagation happened even after that, because we were going beyond the limit. But it took us around like 12 to 14 hours to reach to that.
Mhm. Okay. Yeah, that was my question related to thermal runaway.
Yeah.
Secondly, the matrix that the EV doctor shows, right? In the
Yeah.
demo, you're seeing the health of
Mhm.
the battery, safety,
Mhm.
etc. So,
Mhm.
how do you know the accuracy of the results? What are the benchmark?
Okay, so initially when we were taking the data sets, we were getting around 70 to 80% of the accuracy, because the data sets that we were using were of cell level battery packs. There were only few data sets that were there for the real. Now, when we have got more than 3,000 plus devices on the ground, we are getting all those data sets, and each and every data is being checked with the previous data and the data that is it is currently serving, right? So let's suppose if a guy in Maharashtra is testing battery right now, the same battery is being, or similar kind of a battery is being tested, suppose in Calcutta, right? Those battery packs are being constantly compared during the test itself, because each and every parameters that is being taken during the charging is being sent to the same model, right? To understand how the pack is. So every time a battery pack is being tested, every battery is tested with cross-checked with each other, right? So if there is a healthy battery pack, it is constantly being compared with the low health battery pack data that are there in the model available. So
So
that's
the
why
more
we are
data,
able
the
to get that
better.
conclusion that the battery pack is behaving right.
Mhm.
Yeah.
Okay. Yeah, those were the couple of questions. I have many other questions because, how do you know? So suppose if you are plugging, so this is agnostic of cell chemistry, right? So we can basically plug in any cell. You don't have to know the cell chemistry. You can basically just.
Yeah. So right now it is supporting LFP NMC. We are on the verge
Okay.
of adding other battery as chemistry as well, because see what happens is most of the in the most EV industries, LFP and NMC are the two battery packs right now that are being served to the electric two-wheelers, right? So we are catering to that. Other models are readily available to us with us. We are just in the phase of getting it deployed onto the client end, and right now the accuracy that we are getting in those are around 92.5 or something. that I remember last when I checked. So we are trying to improve that as well, because see, whenever you're introducing a new chemistry to the model, you have to give the context, like this is a different kind of a chemistry, right? It behaves differently. The IR or VI characteristic that you're building is behaving differently. It is not behaving similar to LFP, or where the charging curve is quite flatter as compared to NMC or the chemistry that we're trying to introduce, right? So these contexts, then that takes time, like 2, 3, 4 months is just to make the model understand this is a different kind of a battery pack, right? And these are coming with some failures as well initially when we are testing it. So when we are giving the context to the model, and once it is successful, we are getting a good output or a good accuracy output, then we are deploying that.
Okay.
Yeah.
Yeah. Thank you for answering. It's a really good device, like the whole integration with the app and the hardware. It's
Yeah,
truly
sure.
innovative.
Thank
Thank
you.
you.
Yeah, any other questions? I think somebody else was asking. Okay, fine. If there is any other question, do let me know. You can ping any. I'll send all those the recording as well as the material for reading service related to service and battery and all that over the mail that you have received this link to for. And if you have got any query, you can connect with us at. I'll share the thing. I'll share email ID here. info@batteryok.in. You can share any kind of query. We'll get in touch and try to make you understand, like how do we use battery pack in a better manner. I hope this was a fruitful session for you guys. If there is no other question, okay. Thank you, everyone.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.